Hi people, to finish talking about ideal single-phase transformers, I'm gonna make this video with the goal of coming up with a relationship that will allow us solve problems with transformers. Alright, let's go. Look at the board. Ideal single-phase transformers. At the upper left side, we have a transformer core with two windings wound at each arm of the core. The primary winding has the voltage V1 and the current I1. The secondary winding has the voltage V2 and the current I2. What we are going to focus on this lesson is that there will be no power losses in the transformer. So there will not be losses by Joule's effect and no power losses by hysteresis or magnetization. We are going to let it to the discussion of the real transformer. Now we are dealing with the ideal transformer, so no power losses will be our statement. We are going to trust that there will be no power losses. Alright, if there is no power loss, what then we can say? We can say that the power that will get in the transformer, that will enter the transformer, is equal to the power that will leave the transformer, that there will exit the transformer. P in equals P out. But what is P in? P in is the absolute value of V1 times the absolute value of I1 times the cosine of the angle between V1 and I1, which is represented by theta 1. What is P out? P out is the absolute value of V2 times the absolute value of I2 times the cosine of the angle between these two vectors, which is represented by theta 2. If there is no power losses, theta 1 equals theta 2. Then we can say that the product V1 I1 equals V2 I2. And then we get that relationship on the board. Thus, V1 divided by V2 equals I2 divided by I1. It's mathematics. Alright, but we can say that if there is no power losses, the magnetomotive force that is produced at the primary winding will be transferred to the secondary winding. It's written there under the transformer. F equals R phi. F is the magnetomotive force, R is the reluctance of the core, and phi is the flux. F also equals Ni. N is the number of turns in the winding you are studying, and I is the current at that winding. So, if we say that the magnetomotive is conserved, F1 equals F2. So, N1 I1 equals N2 I2. And then we reach the other relationship that will allow us solve problems with transformers. N1 divided by N2 equals I2 divided by I1. This is what we call the transformation relation. We have there Vi divided by V2 equals I2 divided by I1, which equals N1 divided by N2. It holds for all transformers. If you are solving a problem and this problem says that you are dealing with ideal transformers, you must apply these relationships because they are valid and they help you solving problems. Alright, so now we finished talking about ideal transformers. I hope to make another video about the real transformer, and on this video I will show you the models, the T model, the L model, that will help us solve problems. Alright? These models are a good representation of the real transformer, and when solving circuits you have to use these models because they help us solving problems with transformers. Alright, so it's all for this video. This is the last one talking about ideal transformers. The next one will be about real transformers. So I hope you've enjoyed it. Bye bye.